This session is defeating the transparency features of dynamic binary instrumentation, and your speakers are Xiaoning Lee and Colin Lee. Thank you very much.
Okay, so welcome to our talk. I know we got this lucky time slot right before lunch, so I really appreciate you staying here. We have lots of stuff to talk about, so we're kind of going to start on time. And what we're going to talk about in this presentation is on dynamic binary instrumentation. And first, a quick introduction about ourselves. My name is Kang Lee. I'm a college professor, work at University of Georgia. There I teach information security courses. And my co-speaker, Xiaoning Lee, he is a senior researcher in industry. He has multiple decades of experience in malware analysis. Now, to start, I will give you a really brief introduction about binary instrumentation. So first, about instrumentation. I show you a random piece of code. Okay, you don't really need to read every part of detail. The core part is that I want to tell you that there's a branch, and there's two branches, and what I want to know is when I run with some input, which branch it takes. And for this audience, you can probably figure it out by just read the code and consider the input. For my students, usually when I ask them this question, they will say, okay, let's put in some code. Okay, add to printf, recompile, and run, and see the output tells which branch it takes. The action by putting into all this printf, that's what we call instrumentation. Okay, of course this is the instrumentation with the source code, and likely for this audience you only have binaries. We don't have much of the luxury have source code all the time. You can do instrumentation on binary too. It's the same general concept. And here I show some disassembled instruction, and you can potentially add in code before and after its instructions. And for example, here, if I want to know how many instructions get executed, you can imagine conceptually you can put some counter code before and after instructions. And that's the binary instrumentation. Now, the goal of doing all this instrumentation is observing program behavior. Likely you don't really need to deal with that at the per instruction level. Very commonly you actually do this in the block level. And when I say code block, and I'm trying to illustrate this using a simple graph, and this is what you will see if you take a binary, throw to IDA. IDA actually going to generate this call graph. And in this call graph, each of the block there is a piece of code, and usually you don't have the branch in it. And then based on the execution output, it can go to different code block. And the instrumentation to observe code behavior, usually you just need to do this instrumentation at the end of each of the code block. Okay, this will be enough for you to know how the program executes. And for most of the popular code instrumentation tools, they don't do this directly to the file. I mean, modify the file. If you guys ever patch a PE or Linux ELF file, by yourself manually on the file, it's lots of pain. Okay, so what happens is the tool actually tries to avoid to do that and does all the modification on the fly in memory. Okay, so how does this magic work? The way all these popular tools use is a scheme called code cache. Instead of taking a binary file, run those, load those to the execution part and run them directly, you actually copy the code into a piece of memory called code cache, and all the execution and also the modification going to be done there. Okay, so instead of starting the code run from the first block 1, and your initial code first does the copy, read the original binary code, and then put into the code cache, and along with some instrumentation code after the block, then you run from there. Okay, once it finishes code block, depending on the execution result. Let's say, for example, if code block 3 need to be used, and it will copy it into the code cache, assuming this piece of code has not been copied there before. Okay? If it's there, then you can jump there directly without copying it again. And this thing keep going. Okay? And for example, if code block 3 execution result indicate that block 6 need to be used, and 6, 7 are being copied there, and execution continue, and also all the modification instrumentation can be done in that code cache. without modifying this original piece of binary. Okay, so this is a super brief introduction about how does dynamic binary instrumentation work. And what I want to tell you is, if you're not in this area, I want to tell you is that the use of all this tool are actually, the popularity is increasing. And you can imagine, first I told you that you can use this tool to observe a binary to see how the program runs given certain input. You can also use it to hardening a program, like adding a really special breakpoint, change the program behavior. And this is useful to profile a program and sometime optimization. More likely, like for this audience, it's going to be used to do malware analysis. You want to take a piece of malware, you want to know what it does. So this allows you to trace the dynamic behavior. Okay. And there are lots of popular tools, and this talk is mostly about DynamoRIO. It's a tool now, the developers are all now in Google. And there's also the Intel PIN tool, and there's also the Walgrain. All these are very popular tools. Okay? So with this brief introduction about the background, now let's go back to the core topic. We're going to look at the transparency feature of this DBI tool. What do we mean by transparency? When you use this dynamic binary instrumentation tool to run a program, the platform expects to get the program run as if it's running on the native platform. So you don't want the program to know that here's something run underneath. This is for both the legit program and also for malicious program. And in fact, we do want to give a disclaimer that the DynamoRIO, when they developed at the beginning, was actually most targeted for a legit program. Okay, so they want to make sure all the legit program can run under their framework, and so that there are lots of things they do target for also avoid being detected by the malicious one. But I think their focus more is on getting the legit one run. So that's also sort of make our life a little bit easier, so because they haven't thought about too much about being detected by the attacker. So go back to the transparency. They want to make sure a regular program, if you run on, let's say, on a Windows system, it should also run on their DynamoRIO platform and behave the same way as if it's running on the native system directly. So they actually did lots of special effort. For example, they don't make any assumption about how this code access memory. And this is not only for the malicious code, even for legit code. The developer of the DynamoRIO showed that some of the Microsoft Office program actually access some of the stack frame that are already invalid. And they try to make no assumption on this. So your program is supposed to do anything, then you should not be able to tell you're running under this instrumentation. And I'll give you another example. DynamoRIO, in order to run, if you follow my early slides, it needs to load code from the original binary. It has to have this special loader and has to adding this special instrumentation code. This is all from their own DLL. Now, they didn't load this DLL using the conventional library call from Windows. They actually hide it. Okay, so that if you run a new DLL, the header from the process, you will not find it. So this is also part of the transparency feature they add. In addition to this, there's actually a long list of effort they show, and there are different types of transparency. They want to make sure the regular program will not be able to tell you're under this DynamoRIO or instrumentation platform. The developer even wrote a paper about this. Okay. Now, this is basically the background about transparency. And you can imagine, like, the goal of this DBI tool is try to be invisible, like the invisible man. And our fun job, like the fun part of this talk, is actually try to expose them. Okay, so we try to see, okay, here's an invisible platform when you run, and we actually try to take the role of the attacker, try to say, okay, what if we are the malicious guy? We don't want the people analyze this. We want to anti-debugging. So we show you a couple examples to detect this. The very first one, it's actually a simple idea. If we can run our program, let's say it should run on the regular case in the native platform, but if you run under DBI, it's going to crash. Okay, so this will be like, if you can achieve that stage, obviously you can defeat the DBI. Okay, now how to do this? Well, you can try lots of fuzzing. So here's one example. We wrote a piece of code. This code, what it does is it make a stack pivot. So it use heap as a stack at one stage, and turns out that our code, when we run it, here's a screenshot of run our program twice. The top half of the screenshot is about running this R code without the DBI, okay? And it just ran and shows some output. And the really bottom part is our second run under the instrumentation platform, and then you see there's pop-up window saying, okay, crash, okay? What happens is that when we actually zoom in to look at the code, on the top part is our original code, and you can see there's, for example, the exchange command. That's our stack pivot action. And there's also a push. And when we run the code under the DynamoRIO, and the highlight line actually trigger a memory access exception. And the one additional issue is that DynamoRIO didn't handle this exception well. If they handle the exception well, then we shouldn't see the program crash. And turns out they also didn't handle this exception well, so that caused trouble. We already reported this to Google, and they are aware about this. And by the way, this is just a bug. And now this case is actually a situation that DynamoRIO can fix. Okay, so once they fix the bug, it will not be captured. Later, Xiaoning is going to talk about another more complicated cases about exception handling, which is harder to handle. Second group of attack I want to present is about some simple implementation artifacts. Again, these are the case probably because the developer was not really intentionally trying to hide everything, so we actually just expose this, and by the way, all of this can be fixed. So very first example, if you get your program call to check who is the parent process, you probably will imagine, okay, it's the Linux shell or the Windows command. Well, it turns out it tells you it's the DR run, which is the DynamoRIO program. That's the easy one. And if you look at, for example, the first file handler you got, because DynamoRIO also have to use some resource. If you look at our program under DynamoRIO, we got OX17 as the first handler. And if you run this program native code on the native system, then you got a smaller number. Similar thing, when we run a program on Linux, we try to check what is the maximum number of open file handler. Typically, you will imagine a number like 1024, 496 is power 2. Well, DynamoRIO gave you a weird number like 4,000. Okay, so all those are clue. Some more clue. Like if you look at the memory usage, like obviously because you use this dynamic memory instrumentation, code cache, you're going to use more memory. So with our sample program, we know how much maximum memory to use at peak time. But if under DynamoRIO, it's much bigger. Okay, and other behavior, when we call the setRLimit code, for example, even you try to set the maximum file handler the same number. So right now it's 1024. You can say, let's set it to the same number. In the regular program, this will never fail, and in DynamoRIO, somehow it failed. So we also found this, and Google knows this is a bug. Why it's a bug, we don't know. One more example of all this artifact. Because the DynamoRIO is an instrumentation platform, it will try to observe all the behavior, for example, all the signals sent to this program. So it will try to capture all the signal. Now, for the regular program, say I write a program only care about one say SIGINT, and if you look at the signal mask, it's just only one bit's been turned on. But if you look at the situation running under DynamoRIO, well, almost all the signal mask is enabled. Okay, so that's another artifact. I just want to quickly summarize this: is that all these are artifacts that the developer just probably don't have enough time to handle it. If they want to hide, they can fix all this. I will just try to list those. And one more quick example. If you remember early on, I told you that DynamoRIO tried to hide the library. And in fact, what happened is that DynamoRIO hide the library, but if you try to do a brute force to search all the P header in the process field, and then compare the one you got from the new process module, and you check the list. If it doesn't match, and there's a hidden DLL, and if you also search some fingerprint in there, you might also be able to expose it. Okay, those are some examples that I showed, and most of them are easy to fix. I'm going to let Xiaoning to talk about more fancy examples. Okay, go on.
So now we will talk to different samples. So that's all about the error transparency part. So error transparency is a very important feature for binary instrumentation, because think about the target code always has different exceptions, this kind of stuff. People try to catch the exception by their code. So for binary instrumentation platform, you have to deal this kind of case correctly to make sure the exception can dispatch to the target code correctly. So here we put one simple example. Say this is very typical code to get the current EIP address. So call next instruction pop EX. At that time, EX keeps the current EIP address. So if you put the invalid instruction there, then you will see the exception happen. If you put that within the track catch, this kind of block, you will get the exception record, right? At that time, you will see the EX and the EIP, the distance should be 1, because this is special designed case by yourself. This one, you only can trigger by self-modified code, because this is the bug from the DynamoRIO in the self-modified code. So if you run this case in native Windows, you can see the distance between EX and the EIP, that's 1, right? The BB is the EX value and the BC is the EIP value. If you look at the code in memory, you can see exactly the BB point to the pop EX and the BC point to invalid instruction. That's all correct. So, and also because this is self-modified code, this one should be read-write executable in memory. But if you run this code with the DynamoRIO, you will saw different result. Actually here, you see the EIP will be CC and the EX will be PB. So the distance definitely not 1. So if you look at the code, you can see in memory, the BB still point to the pop EX, but the CC point to fuzzy instruction. So they didn't handle this case correctly. So basically, you can use the distance easily detect your code running in the DynamoRIO. And beyond that, you can see the, because that's running in code cache, so they put the permission for this memory as execute and read only, without write permission. So this one, we filed the bug to DynamoRIO in May this year. They fixed that quickly. So now we have another new case. So that's all interesting. Say the native code never trigger the exception, but if you run that in DynamoRIO, you will get the exception because some bug in DynamoRIO. So the initial idea is, think about, they will move the code go code cache. That means in the code cache, the code eventually have to transfer back to the DynamoRIO engine. If you can calculate the checksum for the runtime running code, then you will get different value from the static code, because the DynamoRIO engine will break the code and move part of code, go the code cache and transfer back. Right? So now we design a very simple case. Say you just guess the current EIP and do some simple calculation to get some checksum, this kind of thing. If you run this code in native mode, you can guess the checksum code and easily without any exception. But if you run this one with DynamoRIO, you can see you will get one exception. That's happened in 26000. Actually, that's invalid memory. We never allocate that. That's the bug from DynamoRIO. They didn't handle that correctly. So actually, we still can do more.
Right, so let me give a quick summary about what's going on here. So we already gave an overview about DBI and the transparency feature. We show about 5 examples you can detect DBI. Now, what can we do from there? Now, you still have to look at from both the attacker point of view or from the defense point of view. For the defense point of view, let's say, if you want to improve all the DBI tool to avoid being detected, there really, first, lots of things to do, at least address all the artifacts I mentioned. Those all can be fixed. However, there are just a lot of those, so it's pretty hard to prevent this completely. So I would say it's a pretty challenging task. If you look at from the attacker point of view, there's still lots of work you can do. We only scratch the surface. We only scratch the surface, like show you, here's a few ways you can detect the DBI. Okay, and if you want to do more, for example, you can do more systematic comparison, between the DBI situation versus native execution side by side. You can probably write a more systematic further to do this. And another thing we didn't touch is that the overhead. Because of code cache, because of the instrumentation, there are additional overheads you add. And so if you can write targeted exploitation, try to just trigger lots of this cold cache overhead, then you might have to also expose it. To quick summarize what we talk about here, and there's the increasing use of binary instrumentation and dynamic binary instrumentation framework, and it's being used in the program observation and malware analysis. And all these tools try to keep transparency, but what we show is it's pretty hard to do it. Okay. Now I do want to say, give some credit back to all the DynamoRIO developer. Even we actually here we're trying to thrashing and say lots of problem about this. They actually developed this mostly targeted to get a legit program to run, and they do also try to hide it, but obviously that's not their top priority. And plus, we actually interact with all these developers a lot, especially Dr. Jin Zhao. He actually took our feedback and also gave lots of feedback to us. And given that we still have time, there's also some interesting thing we find out related to binary, and during our process, I will let Xiaoning talk about all these new findings.
So this is quick material for the bonus part. So actually we do some ROP analysis. So as you know, NOP used frequently for the shellcode pending, this kind of thing. If you don't know what's the exact landing address for your shellcode, this kind of thing. So the non-zero is a very typical one. People use that many times, non-zero, 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 this kind of code to pending a shellcode or similar thing. So now the question is it possible you can create multiple bytes different knobs? That means if you use non-zero, 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 that's very straightforward, but that's every bit repeat, right? It's possible you get 4 different bytes, but still knobs. So here you can see one example. We have 4 different bytes. That's knobs. But the problem is because sometimes you use the non-zero, this kind of thing, because you don't know what's the exactly landing address. For x86, if the different offset, you will decode as different instruction, right? So for this one, you can see if you decode from offset 0, that's not, but if you decode from the offset 1, that's total different instruction. If you use this kind of byte, your shellcode could crash or something could happen. So now, we think about it, is it possible we get some position-independent knobs? So that means you have 4 different bytes, but whatever, which offset you use, you always decode as knob, right? So here's one example. If you use F3, 26, F2, 90, whatever the offset is, you always decode as knob. So how to create this kind of 4 bytes position-independent knobs? So you have a couple different ways. The simple way is you get simple single knob, just repeat. Or you have 2-byte knob, repeat. Or you have 3 and a different combination. And also you have the 4-byte knob, total different one. So here is example. You can use all kinds of different knob bytes here as 2 bytes. And here is 3 bytes. And this is all 4 bytes knobs. So that could be interesting sometimes for people to develop some shellcode pending or something like that. So now we are ready to answer some questions.
Any question about the both DBI and how we break DBI, and also about multiple bytes of knobs? Any of them? If you have questions, you can ask now, or you can certainly find us during the lunchtime. Thanks for your attention.